Welcome back to ECE 442-542. We're in the home stretch of the semester. You have about half of your material completed. Now we have a little bit more than half to complete between now and the end of the semester. We have one more exam, midterm, and one more, and the final exam. If you're thinking about next fall semester classes, I'm offering a technical elective info session tomorrow afternoon at 2. Maybe you've received an email to that effect. That should be in ECE 530, and we'll also talk about the Accelerated Masters program, not AMPS, but the Accelerated Masters program if you're not yet beyond that location in your curriculum to make that decision. Also, things are really packing up, being the end of the semester, and tomorrow or Wednesday's office hours, I'm having to sort of readjust from 12:30 to 2:30 to just an hour from 2 to 3 on Wednesday. Question? I'm going to try to record that and post that. Where I'll post it, I haven't decided yet, but I'll try to let you know. The question was, if we can't make that time, is it going to be available? And yes, if you need a sleep aid, you could open that up and watch that somehow, somewhere. I'll try to record it and make that available. Today, what I want to do is get into what the class title has, Discrete Control Theory. We've been dealing up to this point with discrete, figuring out how to work with things in discrete time. Now we're going to get into the second word of our course title, control, and designing controllers or building compensators. I may call them many different things. I might call it a compensator, I might call it a controller, but that's what we will be doing or working on now until the end of the semester is the idea. Today what I want to do is sort of quickly scroll through, and you'll understand what I mean by that in a minute, but I've already written this down. You can just sort of watch and pay attention, hopefully. Hopefully this won't put you to sleep, but it's stuff I want to quickly get through. You've maybe seen it already, but we'll talk about the control design in an overview perspective. Open loop versus closed loop, the benefits of feedback, what it means to be internally stable for a system. It's not just the external transfer function of the closed loop system that we need to be stable to guarantee everything's going to be well behaved. And then we will get into the direct design by Ragazzini. That's one approach to controller design. Hopefully we will get through that, or at least an example of that. Maybe you don't want to use this, but it might provide us with some insight into what you might want to be doing or thinking about when you're designing controllers. It will start getting us thinking about some of the restrictions or constraints that we have to keep in mind when we are designing controllers. And maybe this will provide you with insight into somebody goes, oh, look at this is going to work. And you design a controller and then you start thinking, why is my system sort of not working the way I want it to? At least you'll know maybe why it's not working the way you were hoping it would work. That's the idea. Let's begin our scrolling. We have a system, and that system, I haven't provided arguments for the input U and the output Y. I've just left those blank. That could be T, it could be Z, it could be N, it could be in the frequency domain or time domain is what I'm meaning. If it's in the time domain, it might be U of T or U of N. If it's in the frequency domain, it might be U of S or U of Z. But you now know how to interpret all of those different forms of this input-output relationship, and now you have a system. That system might be in the form of a transfer function, state space representation in both discrete time or continuous time. But we know that that doesn't always come in the right package or with the right characteristics. For example, maybe it's unstable, and one academic problem that's typically used frequently for an unstable system is an inverted pendulum. So can you stabilize a ruler or a yardstick on your hand? And if you can do that, then you're a good controller, right? How many have ridden a Segway? Just the former president. President Bush, I think, was riding Segways. And they give campus tours on the Segway, so you might, whenever you see that, you might think, oh, that's an inverted pendulum. I know how to control that, or I can control that. You've probably ridden a bicycle. If you just tried to balance, in a sense, that's an inverted pendulum. A rocket is an inverted pendulum, and we try to control that rocket to go from point A to point B and hopefully stay within that particular trajectory from A to B. Those are control problems of unstable systems. Your system might have uncertain parameters. Maybe you're just given a bunch of springs, 1,000 springs, and they're not all going to be manufactured exactly the same. Or you might actually be expending fuel in your rocket, and now your mass is changing as your rocket's flying. How do we deal with that? So your system might have adjustable, uncertain, or unknown values associated with it. And we want to be able to connect a controller to that system so that the closed loop behaves consistently, even though the original system may not be very consistent. And you've seen that maybe in an earlier class with transistors, where maybe you use the feedback concept because the gain of that device may be all over the place. But if you connect it up properly, then it will start to give you a more predictable or effective or consistent input-output behavior characteristic. And that's what we're wanting to do with our controllers. We have these possibly unstable systems, but probably, definitely, a system whose parameters might not be very predictable. Maybe they are in a range, but you want to hit that target every time. You want to make sure that even though your system might vary in the open loop by 100%, maybe you want to maintain this input-output behavior relationship to an accuracy of less than 1% between your input, reference input, and your output. And that's what I'm saying here. Your desire is to maybe collect that open loop system into a new desired system, make that desired system, this is now T sub C, I'm afraid I have a lot of T's floating around. T we use for the sample period, T sub S we might use for the settling time, and now I'm using T for a transfer function. But I'm hoping that you see by context that this has some brackets associated with it, and it's a transfer function. This is a, let's say, T controlled, because this might be a T sub C of S, it might be a T sub C of Z. I haven't yet said, but you should be able to work with both of those kinds of scenarios. We're just going to focus on two types of control structure today and most of the semester, if not the rest of the semester: open loop and closed loop. If you simply want a T sub C of Z, a desired transfer function, and somebody gives you a plant, can you design a compensator, a controller, that maybe just inverts that plant and plugs in what you want it to be? That might be a design. but we'll see that maybe that's not going to work all the time. Or we might have a closed loop design structure, and this should be comfortable to you, or you should be familiar with this diagram. And now I'm referring to this transfer function T sub C of Z between the reference input R and the output Y. And you have to find the transfer function that T sub C of Z corresponds to or is equal to. Let's look at some of these situations that I hinted at before. For example, in the open loop structure, we want this combination of the plant, G, and the controller, C, to be like a transfer function that we want it to be. What are some difficulties that might arise with that? And I don't know if you've heard this word much at all, but in a controls class, in a controls setting, in a controls environment, people are going to be talking about robustness. Is your controller robust? That means, does it work consistently when your plant might vary all over the place in terms of its parameters? Is your system robust? For an open loop system, it's probably not a very robust design, because the parameters in G of Z may, like we said, be unknown, or they might change. And that, if your parameters vary, then your poles or your zeros or your gain or all three might be unknown or moving around or unpredictable. Now how do you control it? Let's look at a very simple case. Here's an example. Suppose this plant is just a constant, and we'll just say it's a little g. Then our desired transfer function between the input and the output is the product. This is open loop again. The product of our system, G, which is just a gain, and our controller, C of Z. Now, if we want good tracking, what does that mean? That means we want the output Y to look like the input R. Meaning, if I have a telescope and I dial it to a certain angle to point at a star, I hope it finds that angle. I hope when I turn it 10 degrees, it doesn't go to 50 degrees. If I turn it to 50 degrees, hopefully it will go to 50 degrees. In terms of driving, you want to be able to tell your car, okay, I want to go 30 miles an hour. Oh, now I want to go 50 miles an hour. It's tracking your input. That's what I'm meaning by a system tracking the reference input. If we have good tracking, then Y, the output, needs to look like R. And so if you had some reference input that's moving around, you want your output to follow that without much error. That's the idea, or that's what we mean by good tracking. If that's the case, then really what we want, we would like that closed loop, I'm always dealing with closed loop, but this is the open loop. We want that transfer function, T sub C of Z, to just be 1. If we want the output Y to look like the input R. And to make that happen, then why don't we pick a controller, C, to just invert the plant? The plant's a constant, G. We can divide by G, and now we have 1. That's now our T sub C of Z. That's what we want. There's always a but. But what if the plant wasn't what you thought it was, or what if it's changing, or it's now a different constant? Maybe this plant is some little device that you're having to control, and it's coming off the assembly line. Now you get a G, you get a G1, you get a G10, you get a G30, you get a G1000. They're not all going to look the same. And you've now designed for 1G. Uh-oh. Now that T sub C, let's say sub 1, is what we thought we were supposed to be getting. 1 over G, we'll control it with 1 over G, but now it came out as a G1. Now we're looking not at 1, but at this new ratio, G1 over G, which really, in terms of a response, if this is where we wanted to be, let's say 10 degrees, because G and G1 are not the same, maybe we get to 7.5 degrees in terms of tracking. And for that reason, Y does not look like R. And there's an error. The error is the difference between where we wanted to be, our reference R, and where we actually ended up with which was Y. So even though we didn't have an E explicitly in our system, we could form an E on paper or in the computer and say, let me compare my reference to my output. In this case, our output was going to be this controlled parameter, 1 over G, times the plant, G1, times R. And that now gives us a G1 over GR, which we can subtract from our reference, and we find that, wait a minute, now there is an error, potentially, between where we wanted to go, R, and where we actually went, Y. And that error is influenced by this parameter, 1 minus G1 over G. That was open loop. Now well, maybe that's not what we want. Let's look at the other scenario, the closed loop case, or when we have feedback. So now when I say feedback, we have that closed loop configuration that we introduced earlier. And this is now the structure that we're dealing with. Does this now help us out a little bit? And I've already hinted that yes, it's going to be better than open loop, but let's see what else happens. So here is our system, and if we simply want to focus on the reference input to the output Y, then we do what with our D, which is a disturbance? We can just zero that out. This is a linear system. If we're interested in what's happening to our error due to a disturbance, or maybe what's happening to our output due to a disturbance, then we could look at that transfer function and let R equal 0. The external transfer function between R and Y is the one that we usually concentrate on, but we have to make sure that our system remains internally stable, which means you better be well behaved. No matter what happens to D and R, E better be well behaved, etc. And Y better be well behaved for a disturbance, D. If I give you a bounded disturbance, you better get a bounded output. There's our closed loop transfer function. GC over 1 plus GC. And that should now be just emblazoned in your head, in your brain, until at least after the final. And if you're interviewing and somebody asks if you've had a control class, and they give you this block diagram, or maybe you draw that block diagram for them and say, oh, we were dealing with this kind of a control scenario, you can say, oh, the transfer function is GC over 1 plus GC. And if you've forgotten, you can just rederive that with some block diagram algebra. Y is just GC times E. The error signal is the reference minus the output. make that substitution, and now you have y is equal to gc times the error, which is r minus y. Do some algebra, pull the y terms to the left, divide by that expression that's scaling the output y, and now we have our controlled transfer function t sub c of z. gc over 1 plus gc. It's the forward branch if we have unity output feedback. Unity, there's nothing but a wire between the output and the summing junction, so it's unity, and it's negative output feedback. With unity negative output feedback, we have this plus sign, and in the denominator we have 1 plus gc. And upstairs we have the forward path, which is gc. What does feedback buy us? Here's an example with feedback. Again, we have a plant that's a constant, G. Suppose now somebody says, oh, I don't know, let's just have a controller that's a constant also, K. Well, we just derived the transfer function between the reference input R and the output Y. That was GC over 1 plus GC. Capital G is just lowercase g, a constant. The controller is a constant, capital K. And now if you let K get big, GK dominates 1. The denominator starts looking like GK. GK looks like the numerator. And that, now you have a ratio GK over GK, and it doesn't depend on G. Now G could be G1, it could be G30. It's still going to be G30K over G30K. And if K is big, we get what we wanted, 1, for this transfer function between the input, reference input, and the output Y. So that now our output tracks our input for large values of gain K. That's what we want. Anybody reading along? If we could cure everything with a big gain, you wouldn't even need to be here for this class. This class would be unnecessary. But then you couldn't command the big bucks when you graduate and saying you've had a controls class. So there has to be more to it than just cranking up the gain K and celebrating. Sometimes you need just a little bit more than that. Sometimes that's all you need is a large gain, and that corrects things, as we just saw in the last example. Here's another but. Let's look at a system that maybe is a little more interesting, has some dynamic behavior versus just a gain. Suppose that our system now is just a pure delay. Suppose Y, the output, is just the previous input. You put in an input, it's just going to sit there in a memory location or in a holding pattern, and now the next time step, that's going to become your output. And let's connect that in this classical feedback configuration and see what happens. Again, let's just keep our controller as a constant K. But this system now has some dynamics. It's a memory. It's just a 1 sample period delay. And what happens? Suppose we want Y, our output, to track a constant, a step. Let's let the reference input be 1, a unit step. And we'll just say, here is our time t equals 0. We can draw that on the piece of paper, or we can paint that on the floor. We can put that in the sand. We can figure out where time t equals 0 is. From that point on, what's going to happen? We know how the output y is related to the input. It's just the input one time step before. Meaning y at time 0 is u at time n equal minus 1. And we're assuming everything was non-energized for this example. U of minus 1 is now k times, well, u is just k times this signal, which is the air signal. And if you're listening at home, you don't know what signal I'm referring to, do you? There. It's highlighted now. But that's the air signal, k times that air, and the air is just r minus y. And that's at the time that we're asking the input to be, and those are now at time n equal minus 1. We said the system was unenergized. Y is 0 prior to time t equals 0. R, we haven't turned it on. Everything in that parenthesis is 0. We scale it by k, we still get 0. U at minus 1 is 0. So that tells us what y at time 0 is. That's okay. Haven't done anything. Now let's turn on the input, or the reference signal. U at time 0 is k, r of 0 minus y of 0. Well, we just computed what y of 0 was. That was 0. R was the unit step. That's just going to be 1 from now on. So the u of 0 is k. And that tells us now what y is at the next time step, y1. y1 is just u of 0, which is k. We're at 0, then we're at k. Now we know how to find u of 1. K times the air. And the air is just r at the time that we're interested in, which is 1 minus y of 1. So we have k times the reference input 1 minus k. Now u of 1 is k minus k squared. And that's going to be what y at time 2 is. Y of 0 was 0. Y of 1 was k. Y of 2 is k minus k squared. Can you see a pattern? Oh, let's find that pattern. U of 2 is k, r of 2 minus y of 2. But y of 2 we just found. That's k minus k squared, which we subtract, and we get minus k plus k squared. Scale that by k, and now u of 2 is k minus k squared plus k cubed. So now we're just alternating signs and raising k to higher and higher powers for each subsequent value of y. So now if you were thinking we could cure everything with k, a big K, think again, right? Now we have dynamics in our system, just a delay. That's about as basic of a system as you can obtain. And now what do we have? As long as k is less than 1, we'll sort of be okay. It may not get us close to where we wanted to be. Maybe we say, oh, let's go to 1, and we end up at a third. But at least that error is not going unbounded. If k has a magnitude of 1, then you're adding 1 each time. 1 minus 1, or so it could be 1, 0, 1, 0, or it could be 0 minus 1, 0 minus 1. It's switching back and forth. at each time step. And if k is bigger than 1, now you're just going to be violently banging back and forth between a big positive value and a big negative value. So we can't solve everything by cranking k up if we have some dynamics in our system. There's our takeaway. We can't cure everything with a large gain. Not all the time. And there's sort of an example. So if we were in a math class and somebody said, oh, you can cure everything with a big K. Now there's your counterexample. So there's an economics example. Maybe that's your budget. Never mind. All right, we want to now we'll slow down a little bit, but we've now figured out that maybe feedback is better than not, but can we figure out what we can do or how to build up that controller based on this interaction of our system and potential structures of these controllers C of S or C of Z. We may not always want to just use a gain. We may have to put some poles and zeros in there. What are some benefits of feedback? Do you remember our segue? Not the transition between one topic and the next, but this device that we might ride. Or a bicycle. If you just had to try to stand on the bicycle and not move, it's not easy to keep it upright, is it? That system may be unstable. Maybe you have this inverted pendulum. Well, feedback's going to allow us to stabilize unstable systems. But all systems aren't generically unstable. You might have a stable system, you just want it to behave better, more predictably. You may want to change the system behavior. And there we really have two main classes of behavior that I want to refer to. One behavior is to improve the transient characteristics or properties. So improve the transients. And what have we used to measure those? Transients. How quick are we going to settle? What's our settling time? Maybe that's not quite fast enough. We want to enhance that. We want to shorten it. One transient that we might be interested in is a settling time behavior or characteristic. Now, is that motivating some other transient properties? What was our robot arm that was moving close to a confined space? Overshoot. We may not want too much overshoot. We may want to improve the percent overshoot behavior of a system. That's a transient behavior. We may want to get quickly to our destination, or we might want to have a quick time to the first peak. We want to minimize our peak time. That's one class of behaviors that we might be interested in, which are transient behaviors. Settling time, percent overshoot, peak time. Another category of system behaviors is how well does Y, the output, look like the input R. That's what I'll call a steady state behavior. can we improve steady state accuracy? And control, if somebody said, describe control in one word, your discrete control class, one word, how would you describe it? Well, maybe it's a hyphenated word. Trade-off. You have to figure out what you can trade off with steady state accuracy versus transient behavior. It's this balancing act, and that's what you get paid for. It's figuring out how to make that trade-off in the best way. You can't always get both necessarily, and you have to maybe sacrifice one for the other. Here's what we might have in terms of a picture. If you were looking at here's time, and maybe this is where we want to go. Let's say this is our desired response, or this is the reference input. Maybe this is R. And I'm not going to say whether it's continuous time or discrete time. It's just maybe a constant. And now you look at what your system does, and maybe your system does something like that. When you say, go to B, it starts oscillating, and it ends up not quite to where you wanted to go. So there's a fair amount of error between your desired response, R, and the steady state output. And maybe it's wiggling more, or maybe it got to that final destination in too long of a time interval. Maybe your settling time was too large. Meaning maybe what you want to do is do a better job of controlling that. And now maybe this red line is a better controlled system. It may actually have zero steady state error, where here is our steady state error. We may want to figure out how to transition from this green curve to a red curve. How do we build a controller to make that happen? And what we have to keep in mind is in the process of doing this, we can't just look at one transfer function. We need to make sure that our system is internally stable. When designing a C of Z, which could be this controller that we're interested in, we need to make sure the system is internally stable. In addition to, let's say, stabilizing this external transfer function, which we were calling T sub C of Z. And do you remember what the transfer function of that was? Between R and Y, which I said needed to be emblazoned in your noodle. And since these are scalar, you could do these G's and C's commute. So you could say GC over 1 plus GC. or you could say CG over 1 plus CG. It's the same thing, since we're dealing with scalar transfer functions. So let's say this is G C over 1 plus G C. We not only need that one to be stable, so we're now looking at the zeros of 1 plus G of C, C of Z, but we also need to ensure that we have 3 more transfer functions that are stable, or they're bounded input, bounded output stable. For internal stability, we need the following transfer functions to be bounded input, bounded output stable. And maybe I should put the diagram in front of us so we can keep track of what we're dealing with. We might be interested in the transfer function between the reference input signal and E. Meaning if I inject a bounded reference input signal R, I better get a bounded output at the air. That's one of the transfer functions that we're interested in. We also want to be able to ensure that if we inject, or if a disturbance occurs, maybe we are designing a cruise control and now the car goes up an incline, that's like a disturbance. That incline now is a disturbance input because that's different than what we're controlling with our own pedal. We want to make sure that the transfer function between D and Y is stable. And we also want to have our input signal well behaved when we inject a bounded input at the reference. So our reference input better produce a bounded input to our system in order to be internally stable. And if you look at and do the block diagram algebra, now you have this, let's say, transfer function between the reference input R and the air signal E is 1 over 1 plus CG. We need that one to be stable. We need the transfer function between the disturbance and the output Y to be stable, and you can rederive these in your leisure tonight. G over 1 plus GC, that's not the same as GC over 1 plus GC, and this one between R and E is not GC over 1 plus GC, is it? And the other one that we said we wanted to have stable was this transfer function between the reference input and the input U to our plant. U over R is now C over 1 plus CG. Now if you look and compare that with our external transfer function, this was the transfer function between what? What was the input? The reference. And what was the output for that transfer function? The output, Y. That has the same denominator, doesn't it, as all of these, 1 plus CG. But they don't all have the same numerator, and so we might have cancellation issues between one and the other. Meaning if we try to make 1 plus GC nice, that may be well and good for our external transfer function, but we may have some issues when we look at the cancellations that we might try to create when we're designing a controller C of Z just from the external transfer function T. Question? So now we have talked about a noise on the sensor here, and that was the question. You can show that it will eventually boil down to or give rise to these same kind of transfer functions, or one of those. So we're just going to focus on these three. If these three are bounded input, bounded output stable, then our system, we will say, is internally stable. Because of the difference between this numerator and these numerators, we're going to have some differences in poles and zeros in these transfer functions. And we want all of those transfer functions to have their eventual denominator to be having its poles where? In this class. Inside the unit circle. That will give us a bounded input, bounded output stable response. Now, instead of having to check all of these every time you design a controller, we can sort of get away with achieving internal stability under the final, or under this condition. We can achieve internal stability when we're designing this controller C of Z if we keep that controller C of Z from canceling unstable pole and zero factors, in G of Z. Meaning if you had an unstable system, you can't build a controller C of Z and maintain internal stability if that C of Z actually tries to cancel that unstable pole in your original system G of Z. Or if you have a zero in G of Z that's living outside the unit circle, and for whatever reason you say, oh, I'm going to cancel that with a pole in my controller. No, no, no. That cost you 50 points out of 10 on the exam. So this is what you need to focus on. If you think, well, I don't know how to stabilize my system unless I cancel something outside the unit circle. Say, no, 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 I can't do that, so I have to figure out what's going on. So we'll figure out ways to maybe give us some insight by doing state space designs. Maybe you look at this and you go, I have no idea how I'm going to control this system. Well, we'll go into a different domain and try to build a compensator using different techniques. And then we'll go, oh, why didn't I think of that? And that will then guide you in how to maybe design transfer function-based controllers. That maybe that's how you originally started trying to build a controller. So this is another take-home message for the day. When you're designing controllers and you just want to cancel something outside the unit circle, just forget that, okay? Don't do that. No, 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 no. Don't do that with your controller. Don't cancel a zero. Don't cancel a pole. You'll just have to try to pull them back into the unit circle some other way. Okay, you can't go canceling them, because that will then come back to bite you, because then you might have an unbounded U, or you might have a disturbance now, a constant disturbance. Now you go up a hill and your car goes unstable. That's kind of stretching it, but gives you the idea. Now that we have an idea that we want to make probably the output Y look like the input R, we want to stabilize our system, and we want to do it in a timely fashion with maybe a short settling time, a nice overshoot behavior. What we want, and we want to do it knowing we can't cancel things outside the unit circle with our controller. Let's look at some ways that we might do that. And here's our first strategy. It's the direct design by Ragazzini. I just wanted to do that because of the name, right? But this is an individual that had a textbook. I think you guys were probably around 1958. Oh, maybe not. A few years ago. But he came up with this strategy. So it's the direct design method of Ragazzini. And the reason I like to start with this is there's several reasons, but one is hopefully now you know how to build, or you now know how to specify. If somebody gave you the choice and said, give me 2 poles in the Z-plane that you want your system to possess, you now know how to find those poles based on different conditions, right? We have our Cupid spec. Bullseye and a heart, right? So the bullseye is settling time, and the heart is percent overshoot. So if somebody gave you percent overshoot spec and a settling time spec, those are the Cupid specs, and you now know how to make those happen with 2 dominant poles inside your unit circle, right? You know how to find an R, and you know how to find the zeta. The zeta would then be translated into a theta sub D. Now you have your Z sub delta, your desired poles, in terms of an R, a polar form, radius, and angle. And that would be your denominator of your T sub C of Z, your dominant dynamics. Then you would make all your others quicker, which means what? Let's say your T sub C of Z needed to be 4th order, and you now have, from the Cupid spec, you've picked 2 of those. And those are supposed to dominate your behavior. Where do you locate the others if those are supposed to dominate? Dominate actually means to move slower than the rest. You want your other poles to be faster than those poles that are dominating your response. And if you want poles faster than your dominating poles, where do they need to be in the Z-plane? Closer to the origin, don't they? They need to be inside a smaller bullseye, or inside a smaller concentric circle inside the unit circle. So your dominant ones, let's say, are at 0.95. Now you want to be inside that a fair amount, so that maybe you're 5 times, 10 times faster with those poles than your 0.95 poles. And that's where your other 2 poles would be. Because you had 4, you needed to specify. One thing about discrete controllers is we can actually put poles right at the origin. And then we end up, if all the poles were at the origin, we would have a deadbeat response. It's a term. A deadbeat response means that in a finite number of sample periods, everything's going to be gone. Your error will be vanished. It's deadbeat. You beat it to death. Your error. All right, so you're learning all sorts of terms today. Robust and deadbeat. Well, they use deadbeat in a negative way in the media, don't they? Deadbeat parent. But we use it in a good way here. It's a deadbeat controller, or a system that's now has deadbeat behavior. All your poles are at the origin. Where was I? Oh. First thing we need to do is find a desired transfer function. That's the first step in the direct design by Ragazzini. So I will say, let's create or design, since that's kind of in vogue. We want to design. So now you can get out your crayons and start designing your T, your capital T sub C of Z. So we're going to design, we're going to create or build a desired closed loop transfer function. And now at least you know how to think about the denominator of that beast. Dominant poles might be specified by R, theta sub D, zeta, settling time, percent overshoot, peak time. Peak time gives you what? An angle in the z-plane that you might need to be beyond if you want a quick response. Well, that seems pretty easy, but here's a big caveat. We can't just arbitrarily pick a T sub C. T sub C of Z. That's why, again, you're taking this class. You need to figure out how to build it. So certain restrictions, and I'm not going to go into those just yet, because I want to make this a two-step process. So certain restrictions will be placed on T sub C of Z. So don't forget that. But once you have T sub C of Z built properly with the appropriate restrictions, then it's just turning the crank to find your controller. Then we can simply compute the controller that makes T sub C of Z happen. And I shorten that to just say realizes. Compute the controller that realizes T sub C of Z. Where T sub C of Z, remember, we know what that looks like because it's emblazoned in your noodle, right? That's just this G of Z, C of Z over 1 plus G of Z, C of Z. So if you wake up in the middle of the night and you scream out GC over 1 plus GC, you can just go back to bed and dream some more, okay? Because you're in the right place. GC over 1 plus GC. Now, what does C look like if it makes T sub C happen? Well, we can just do the algebra. So now let's now solve for C from this relationship. T sub C, we're going to build. We're going to design that based on the design specs and certain restrictions. So we're going to have that in our hand or on our paper. We're going to have possession of T sub C of Z. We have our plant, G. We're now trying to find what is C. So let's just solve this for C. That's all we're doing. And that will be our design equation. Meaning, let's just cross multiply. And I'm going to get quick and not include the arguments. So that T better be T sub C. It's not the sample period. So by context, you know what T is. And this is now equal to GC. But that's now just T sub C plus GC T sub C equal GC. And aren't you glad you learned algebra? But these G's and C's are rational transfer functions, aren't they? They're more than just variables, but that's okay. Now we can, let's put all of our terms that involve C. We're trying to solve for C on one side. So T sub C can stay on the left, but let's pull that GC T sub C to the right. And we now have GC minus GC T sub C. Well, there's a common plant in those, so I have a G, and this is now a C minus C T sub C. Oh, good, there's a common C. So this is now G, 1 minus T sub C, C. A lot of C's and G's and T's. I better enunciate better, huh? Especially if you're at home. You don't get to see, well, you can see the board, most of it. Now we just have to solve for C. And these are all rational transfer functions. They're scalar. We can just solve for C. C of Z, now I'll put it back in, is, let's just divide by G by itself. And G, remember, is our plant. So we now have 1 over G of Z. And we also have T sub C of Z. That we have on our paper, 1 minus T sub C of Z. This is our direct design formula. Which, if you have your T sub C created or built, and you have your plant G, you can just turn the crank. I mean, it's going to be some algebra, but you can solve for this transfer function C of Z, which is your controller. And what are you doing? Well, one of the things that you're kind of wanting to do is indicated right there. What did we say we like to do even in an open loop setting? It'd be nice to invert the plant. Just cancel the plant, wouldn't it? We can't do that completely, because if we're inverting the plant, and if that G has poles or zeros outside the unit circle, what did I say you can't do? You can't cancel those. So your C better not have any of those unstable poles and zeros that you're trying to cancel. So we can't just blindly invert the plant. We have to somehow make sure that this combination of the ideal, T sub C over 1 minus T sub C, this is where the restrictions or the constraints come in on T sub C, it has to be designed in such a way that C of Z doesn't cancel unstable poles and zeros and certain other properties. Let's look at the first property that we need to have for our ideal T sub C. So here I will call these restrictions. And we have restrictions because we want C of Z, it cannot do the impossible, our controller. It can't make our system non-causal. We're in a control environment. It doesn't have a magic 8 ball or whatever. It can't see into the future, our controller, unless you know something that I don't. If you do, then come see me and we'll, I don't know, keep it hidden. Okay, we won't give it away. We'll be like the Coca-Cola formula. It'll be a trade secret. We won't patent it. We'll just keep working. C of Z cannot do the impossible. That's the reason for these restrictions. Restriction 1. C of Z, let's now parameterize that as some numerator. The notation is N for numerator, D for denominator, and those are polynomials. These aren't rational expressions in Z. These are just polynomials, and they are polynomials associated with our controller C. That's the subscript C. So this is N sub C, numerator of the controller, D sub C, denominator of the controller. That controller must be causal. Like I said, it can't see into the future, so it can't build the present signal going into the plant based on future errors. It's not that smart. Okay? Although you might think it is when you design it, since it's your design, but it has to be causal. And another way of thinking about that is C of Z cannot have a pole at infinity. Or as Z marches off to infinity, C of Z better not get big. So C can't blow up as Z marches off to infinity. Or what does that really mean? We really need the degree in order for C of Z to be causal. What's the relationship between the degrees of the denominator and the numerator? Is there a relationship? We want C of Z to be causal. What does that mean in terms of the degree or order of the numerator polynomial and the denominator polynomial? So now you can say whatever you want, right? Because you could say, oh, bigger than, less than, and you could say, oh, well, I was meaning this versus that. Right? So you could sort of hedge your bets by saying greater than. What's greater than? Well, we need the denominator to be bigger in degree than the numerator. Let's look at the case when that's not the case, or the situation. So here, let's look at an example of a violation and why that leads to a violation. So here, this example is, we are going to show what happens when the degree of D sub C of Z is strictly less than the degree of the numerator. So that we can believe this condition. Well, if we want C of Z to have a pole at infinity, then we could make that happen more easily than what I'm doing it, but let me just build it up a little bit bigger. Let's say that I have a z squared minus 3/4 z plus 1/8. And if you're good at factoring, you know where the zeros are, right? They're at 1/2 and 1/4. So we have a 0 at 1/2 and 1/4. I have no idea where that pole is. The pole is at 1/8. So we have no pole zero cancellation. We have a pole at 1/8, and we have two zeros. It's not so much where those are located that's important. What's important is the degree of those. And in this case, the degree of the numerator is strictly bigger than the degree of the denominator. That's clear, isn't it? Have a second order versus a first order. So what does this give us? Well, remember what C is. We could write this in terms of delays. This is written in terms of advances, isn't it? But if I write that in terms of z to the minus 1s, I can do that by multiplying by a 1, where my 1 is a special 1, z to the minus 2 over z to the minus 2. That gets rid of my biggest power of z. If I scale that way, I now have 1 minus 3/4 z to the minus 1 plus 1/8 z to the minus 2. Downstairs, what do I have? Is that okay? I just hit it with 1, where my 1 was special. Now, I want to remind myself what C of z does. That's a mapping from the air into the input that drives the plant. My input is down below, that's my air, and the output of that subsystem is up above, and that's my input to the plant. So this is the transfer function between the air and the plant, and the input to the plant. If we cross multiply, then we have z to the minus 1 minus 1/8 z to the minus 2 times u of z, and I just did this so that I could have my u's on the left, but I hope you can sort of do this mentally. And now I have e of z being scaled by 1 minus 3/4 z to the minus 1 plus 1/8 z to the minus 2 times e of z. Let's go into the time domain. That's the frequency domain, but now we can push that into the time domain. You should be able to do that in your sleep, right? You were dreaming about GC over 1 plus GC before, so now you can really do this. Which means on the left we have u of n minus 1 minus 1/8 u of n minus 2. That's equal to e of n minus 3/4 e of n minus 1 plus 1/8 e of n minus 2. Does anybody see a problem? U is the signal that's driving our system, our plant. That's the input. Let's just substitute in a convenient value for n. Well, maybe I want to think about u at the present time, so let me let n equal 1. U right now, the input right now, is a function of the input one time step before, the air when. What was n? 1. What? The input now depends on the air when? in the future. This is not Back to the Future. We can't be doing this, can we? We don't have our whatever car to get us back to the future. Maybe we can build one. Like I said, if you know a way to do this, let's talk. But what is this showing? I hope this is showing that because of these two pieces right there, this leads to a non-causal control law. And what does that really mean? I really didn't even tell you much of the restriction, but the restriction says that if you have a pole zero excess in your plant, your T sub C of Z has to have at least that same pole zero excess. That's the idea. That's restriction one. You can't make your system faster than it began in terms of, you can't speed it up that way.